Have you ever really stopped to think about how the device you're watching this on actually thinks? I mean, it feels like magic, right? But it's not. It's actually the result of a quest that's thousands of years old, this deep, universal human need to count things, to calculate, and just manage information. Today, we're going to pull back that curtain and see how it all works. Okay, so to really get our heads around the modern computer, we have to go way back. I'm talking long before electricity, long before silicon chips. The first steps toward what we call computation weren't taken with circuits, but with things like gears, beads, and some really brilliant mechanical ideas. And this is where our story kicks off, with the abacus. We're talking nearly 5,000 years ago. This was, for all intents and purposes, the world's first mechanical calculator. No, it couldn't do your taxes, but for basic adding and subtracting, this simple little frame of beads was an absolute game changer for trade and keeping records. So for thousands of years, calculation was pretty much a hands-on process. But then, in 1642, we get a huge leap forward. This young genius, Blaise Pascal, creates this thing, the Pascaline. It was one of the very first machines that could truly automate math. It basically took the idea of the abacus and turned it into this incredibly complex, clockwork-like calculator. But you know, the biggest jump didn't come from just building a better calculator. It came from a whole new idea. And for that, we have to talk about this guy, Charles Babbage. In the 1800s, the age of steam and iron, he dreamed up something that was just mind-blowing for the time. He imagined a machine that you could program. Yeah, the direct ancestor of the very screen you're looking at right now. Babbage actually designed two amazing machines. The first one on the left there, the difference engine, was basically a super specialized mechanical calculator. But his real masterpiece, his true legacy, was the analytical engine on the right. He came up with this in 1837, and it wasn't just a calculator. It was a general-purpose programmable computer. It had a mill, which was like a processor, and a store for memory. In every important way, this was the blueprint for the entire digital age. So the big question is, how did we get from Babbage's mechanical dream to the electronic world we live in today? Well, the genius behind his whole concept, and of every single computer ever since, is that it all boils down to this really elegant and, believe it or not, surprisingly simple process. When you strip everything else away, this is what a computer is. It's a machine that takes in some data, does something to that data based on a set of instructions, and then shows you what it did. That's it. That's the whole game, right there. And this is it. This is the fundamental cycle that makes it all happen. It powers every computer, from those old room-sized giants to the phone in your hand. Input, process, output, and storage. These four steps are the absolute core of computing. So let's break them down one by one.
All right, let's start at the beginning. Input. This is all about how we talk to the machine. It's how we give it data, how we tell it what to do. A good way to think about it is that these are the computer's senses. And just think about all the ways we do this every day. We type on keyboards, we click a mouse, we talk into a microphone, we scan a QR code. Every single one of these devices is like one of the computer's senses, translating what we do in the real world into digital information that it can finally understand. And sometimes these inputs can get really, really specific. Take micro, for example. You've definitely seen these funny-looking numbers at the bottom of a check. Well, they're printed in a special magnetic ink, and that ink allows a machine to read them, processing millions of checks super fast and accurately. It's a perfect example of an input designed for one critical job in our banking system. Okay, so we've given the computer some input. What happens next? Well, now we get to the most important part of the whole cycle, the process. This is where the actual thinking happens. This is the computer's brain. And that brain has a name, the CPU, or Central Processing Unit. It's really made of two key parts. You've got the control unit, which is like the traffic cop, grabbing instructions and telling all the other parts what to do. And then you have the ALU, the arithmetic logic unit. That's the calculator. It handles all the math and all the logical decisions, like, is this bigger than that?
The way the CPU works is by following this simple four-step dance, just relentlessly. It fetches an instruction, decodes what it's supposed to do, executes the command, and then stores the result. Fetch, decode, execute, store. And it repeats this loop over and over and over again, literally billions of times every single second. It's incredible.
Now, of course, a brain is no good without memory.
Computers have two main kinds. First, there's RAM. Think of RAM as your short-term memory, or like a temporary desk you're working on. It holds whatever you're doing right now. But here's the catch. When the power goes off, poof, it's all gone. That's why they call it volatile. ROM, on the other hand, is like the computer's permanent instruction manual. It holds the core stuff, like how to boot up. It's non-volatile, so it remembers even with no power. And over the years, this whole memory family has evolved. In the world of RAM, you've got different flavors like SRAM and DRAM, each one balancing speed and cost. And the ROM family has gotten way more flexible too. Early ROM was written once, and that was it. But newer types, like EEPROM, can be electrically erased and rewritten. That's exactly how your phone gets those important firmware updates.
So let's recap. The computer took our input. The CPU processed it using memory. The third step in our cycle is output. This is it. This is where the computer shows us the results of all that work. It's how it talks back to us.
And it usually talks back in one of two ways. A soft copy is the digital thing you see on a screen. It's temporary. A hard copy is the physical version, something you print out. So one you see, and the other you can actually hold in your hand. And these devices are the computer's voice, its canvas, its way of communicating. Monitors show us pictures, speakers give us sound, printers put it all down on paper. They are the essential bridge that makes all that invisible processing actually useful to us. So when you pull it all together, you see this absolutely incredible journey, right? It starts with a simple mechanical tool for counting, then becomes a revolutionary concept for a programmable machine in the 1800s. And finally, machines like the UNIVAC bring that idea to life with electronics. But here's the most important thing to take away from all this. That simple, elegant cycle, input, process, output, that was dreamed up in principle over a century ago, that is still the fundamental heartbeat of every single computer today, from massive supercomputers to the one in your hand. I mean, just look at this. On one side, you have the massive ENIAC, one of the first electronic computers ever. On the other, the ancient abacus. The technology couldn't be more different. But the core idea, taking in information and processing it to get a result, it's exactly the same. It's kind of wild when you think about it.
And that kind of leaves us with this one huge, fascinating thought. For all of history, we have been the ones telling the machine exactly what to do in that process step. We write the instructions. But the next great leap in computing is already here. It's one where the process itself starts to learn and write its own instructions. And that changes everything.